Hello, Charles.
Hi, Michael.
How are you today?
I'm doing just fine. How are you doing?
All right. I'm a little bit out of practice with this lecturing thing, so I hope this goes well.
I'm absolutely sure it will.
So today's lesson is continuing what you were talking about in terms of game theory, but I'm going to be focusing in on what happens when you are worried about making decisions with more than one player in a sequence, which we started to get into at the end of your discussion, but I'm going to go more into it.
Okay. I really like the logo, by the way.
Thanks very much. Yeah, it's a specially designed game theory logo.
I like it very much. I like it very much. I will point out, however, that all sequels should be called The Quickening.
Yeah, I was going to go with The Quickening or Judgment Day, but I didn't think that made any sense.
That's a fair point.
So let me take you back into what we were talking about last time. We were talking about the iterated prisoner's dilemma, and here's the prisoner's dilemma payoffs that you wrote down for us. Do you remember this?
I vaguely remember this.
And remember, it was about these two criminals, Smooth and Curly, and they were deciding whether to cooperate or defect against each other after they've been arrested.
Right, and they defect. They always defect.
They always defect, right. So in particular, we said, well, what happens if they have multiple rounds in which to interact? And so here they are, here are the two of them, and if they got one round to live, we did an analysis and we indicated that there's really nothing they can do other than defect against each other. It just is irrational to do anything else.
Yep.
So we said, all right, well, what happens if we allow there to be more than one round? So now we've got 2 rounds, and what we realized was that if you've got 2 rounds to go, then these players essentially face a 1-round game, because after this round, what they're going to do in the last round has already been determined. So it's almost as if that round doesn't really matter. There's nothing we can do now that's going to change what they're going to do in that last round. So it's sort of like there's just 1 round, and we're going to defect again.
Right. So life is terrible, and everyone is out to get everyone else.
Exactly. And not only is it for 2 rounds, but this same argument continues as you go 3 rounds or more.
Oh, it's like a proof by induction.
It's kind of like a proof by induction. Yeah, well, it's proof by ellipsis.
That's my favorite kind of induction, proof by ellipsis.
So the question then becomes, what happens if the number of rounds left is unknown, right? So what we realize is that if you know how many rounds are left, the whole thing comes unraveled and they're just going to defect forever. But we raise the issue of what happens if the number of rounds left is unknown. And it seems like it shouldn't really make any difference, because if it's, say, some finite number, we just don't know what it is, then it seems like it should just still reduce to the same setup that we have. So I was looking into this, and it turns out that is it's not the case. It actually does make a difference, and it's really interesting how it goes and how it connects back with other things we've talked about.
Ooh, tell me more.
So here's how I started to think about it. So let's say, how can we represent the idea that we have an uncertain ending? Well, one way would be if we had some kind of generic probability distribution over the number of rounds that the game's going to be played. But this seemed like the simplest idea that I could think of. So here we have our 2 criminals, and what they're going to do is they're going to play a round of Prisoner's Dilemma, but at the end of that round, they're going to flip a coin, and with probability 1 minus gamma, that will be the last round. It's all over. But with probability gamma, they're actually going to play again. And they do this after each round, and so each round is basically statistically independent of the other rounds.
I see.
So the setup here is with probability gamma, the game continues. Now, notice that I chose gamma here. This was it's representing a probability here, but in the past we've used this to represent a discount factor. But that actually is the same thing, right? In the normal discounting, we say that the value that you get 1 step from now is discounted downward by gamma, and that's exactly what you'd take if you worked out the expected value of a game where you continue making steps with probability gamma, and with probability 1 minus gamma, it ends and you get 0 from then until the rest of time. So every round here could be your last, or not, right? It could be that you actually get to continue playing. Does that make some sense?
That makes perfect sense.
Awesome. All right. So this is exactly that kind of situation where, well, here, let me ask you a question. What's the expected number of rounds of this game?
Well, I'll bet it's finite if gamma's less than 1.
Yes, I even wrote that down.
Yeah, I'm smart. Or at least I can read.
Sure, but but specifically, we can actually write it as a function of gamma.
Let's see. If gamma were something like 99%, then I would expect it to be about 100, right?
Yeah, I think that's right.
Yeah.
So is that your answer? My function of gamma is, if gamma is 0.99, the answer is 100.
Yeah, something like that.
It's not a total function, but it's a function.
Well, it's a sample. I mean, you do machine learning. Why don't you tell me what the function would be given that sample?
Well, we can make it a quiz, or I could just tell you.
Why don't you just tell me?
All right. So 1 over 1 minus gamma is the answer. It works for your example. 1 minus 0.99 is 1/100th, and we're talking 1 over that, so that you get 100. And yeah, we could go through the argument as to why that's what it is, but this 1 over 1 minus gamma is what shows up all the time. If gamma is 0, then we're talking about 1 over 1. The game lasts one round. That's exactly what we'd expect. As gamma gets closer and closer to 1, this quantity is getting closer and closer to infinity.
Right.
So, in fact, if it becomes unbounded as gamma hits 1. So, so this is the expected number of rounds. And so that means, so as you said, if gamma is 0.99, it's 100 rounds. And we already reasoned that at 100 rounds, the whole thing falls apart.
Right. Huh. And I noticed the 1 over 1 minus gamma, of course, is just like the way we did discount factors when we started doing MDPs in the first place.
Exactly. Yeah, that kind of links them together.
That's actually kind of neat.
So if we're going to be talking about strategies in this game that has an uncertain ending, we can't just write down sequences of actions anymore. We can't just say cooperate, defect, 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 or even some kind of tree of possibilities, because those are going to be finite representations. We need some other representation that allows us to play for an unbounded number of rounds. And I'm going to start off by presenting an example of such a strategy, one that's very famous for the iterated prisoner's dilemma, and it's called tit-for-tat. And the structure of tit-for-tat goes like this. On the first round of the game, a player playing this strategy will cooperate, and then in all future rounds, the player is going to copy the opponent's previous move. Does that make sense?
It does. So basically, I start out acting as if you're going to cooperate with me, and the moment you don't cooperate with me, I will start to defect, and we'll be in the old-style prisoner's dilemma, right?
Well, no, not this. What this says is it actually copies the opponent's previous move. So if an opponent goes cooperate, defect, cooperate, defect, cooperate, defect, 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 cooperate, 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 you're going to see something very similar coming out of the tit-for-tat agent.
Oh, I see.
In fact, we can represent the strategy as a little finite state machine like this.
I like that.
And so you can see exactly how it kind of proceeds. It starts off cooperating, and then in each round, it waits to see what the opponent does. That's the green letters here. And then it follows the corresponding arrow to determine whether it is going to cooperate or defect in the current round.
Sure, that makes sense.
So in this picture, the black letters here represent my move, and the green letters represent my observation of the opponent's move, or at least if I'm being tit for tat.
What happens if we follow tit for tat?
That's a great question. So let's make it a little more concrete. So here's a set of strategies that an opponent might adopt. And now the question is, what does it look like tit for tat is doing in response to each of these? And I just was hoping that you'd check the corresponding boxes. So basically, for each row, say, okay, if tit for tat is playing against always cooperate, what does tit for tat do? Does it always defect? Does it always cooperate? Does it cooperate and then defect, 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 defect? Does it alternate between cooperate and defect? And this should give you some practice in interpreting the behavior of tit for tat.
Okay, that works for me. I think I could do this.
Go. All right. So let's start off. Maybe you can tell me what happens when tit for tat plays against always cooperate.
So what happens if you always cooperate? Well, let's see. I start out cooperating. And since the other person is cooperating, I will continue to cooperate because that's what they did the last time. So I will always cooperate.
That's right. Good. All right. So what about if we play against always defect?
Well, if we always defect, the first time I'm going to cooperate because that's what you said tit for tat is. But from that point on, I will do what my opponent does, which is defect. So I will cooperate and then defect, 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 ellipsis.
Yeah, so I put this always defect in there, but it can't ever be the right answer, right? Because tit for tat always starts off cooperating. So the other three seem like they might be possible. Always defect is not possible. Good. All right. So what if tit for tat plays against another tit for tat?
Well, I started out cooperating. My opponent cooperated. And since I'm going to do what that person does, I will cooperate. But since that person's doing what I did, they will also cooperate. And so we will both cooperate forever. So we will always cooperate.
Nice. So isn't that kind of interesting? So tit for tat, even though when it's playing against itself, is a very cooperative fellow. But if tit for tat is playing against something that defects, it becomes a little bit more vengeful.
Yes.
All right, so what if it plays against something that is a little unsure of itself? So it starts off defecting, then cooperating, then defecting. Then it's sort of almost an anti kind of thing, right? So this is one that starts off with a defect.
Right. So first thing I do is cooperate, and then after that, effectively, I do what the opponent does one step before. So I basically take I'm pointing to the screen. You can't see me. I take the DC, DC, D, and I just put a C in front of it because that's what I'm going to do. So I will do CD, 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 ellipsis. So that's your last choice.
Isn't the CD, CD, CD ellipsis in Atlanta?
It is, actually. It is the home of all such analysis of diseases in the United States.
The Center for Disease Control? Is that what it's called?
That's exactly what it is. Come to Atlanta and work for us.
All right, so good. So that's the pattern of responses that tit for tat makes against this set of strategies.
Oh, so we answered my question.
All right, so now that we have a sense of what tit for tat does against various strategies, let's try to think about what we should do against tit for tat. So what do we do if we're facing tit for tat? So I'm just going to break it down to two possibilities. It turns out there's actually more, but these two are pretty instructive. So let's pretend that we have to choose between always defect as a way of playing against tit for tat, or we have to be always cooperate playing against tit for tat. So what I've written down here is what the total discounted reward is going to be, or the total reward in this case, as a function of gamma. So let's start with what happens if you play always cooperate against tit for tat. Well, you already told me that such a thing will result in tit for tat always cooperating.
Mm-hmm.
And that means that we're going to play in this box, the cooperate box. And that means on every single round we're going to get a -1, which means over an infinite run we're going to get an average of -1 over 1 minus gamma.
Mm-hmm. That makes sense.
You agree with that?
I do.
Just it's -1 repeated over and over again. Now, always defect, as you recall, you told me that will result, well, for the always defect agent against tit for tat, the first thing that's going to happen is it's going to defect while the tit for tat cooperates, right? So we're going to get 0 for playing that strategy on the first round. And 0 doesn't sound very good, but look at the alternatives. They're all negative. So 0 is pretty good.
Mm-hmm.
So it does this sort of good thing in the first step. Then after that, tit for tat responds by always defecting in response, right? And that means we're going to be stuck in this box, the defect box. We're going to get -6s for the rest of ever.
Yes.
So that means -6 over 1 minus gamma, but that starts one step from now, so we multiply it by another gamma.
Okay.
All right? So these are two different expressions that represent what our payoff will be for adopting two different strategies. And in fact, if gamma is really high, very close to 1, then this is a really good answer, right? Because it sort of grows, it's like -1 over 1 minus gamma. So for high gamma, we're talking about something that's -1 times a really big number.
Mm-hmm.
Whereas this first one is not so good for high gamma because what's going to happen is it's going to end up getting -6 on every step. So it's going to do worse overall. But if we're talking about a low gamma, then let's say 0, for example, a gamma of 0 will always defect will get 0 plus 0,
Right.
but always cooperate will get -1 over 1, and 0 is better than -1. So for really small gamma, like if the game's unlikely to last many rounds, you should defect. But if the game is going to last a long time, then you should cooperate.
I believe that.
Cool. All right. So then my question to you is, what's the value of gamma for which these two different strategies to play against tit for tat are equally good?
I think I know the answer.
Whoa, that was fast. Let's give everybody else a chance to think about it.
Okay.
Go. All right, Charles. What you said you have the answer. How do we figure it out?
It's 1/6.
I guess that's which we don't. I don't know if it will accept that. It's whatever 1/6 is expressed as a decimal. But yeah, 1/6. How did you get that?
I saw the number 6 and figured it had to be 1/6 because you said it was low. But here's what I actually did while I was thinking about it. Is you said, well, when are they equally good? Well, if you always defect, you get -6 gamma over 1 minus gamma. And if you always cooperate, you get -1 over 1 minus gamma. So they're equally good when those two values are the same.
Good. All right. And the denominators are the same. As long as gamma is not 1, that's fine.
Right.
If we divide by the -6, we get gamma equals a sixth.
Exactly.
Excellent. So that's interesting, right? So it's saying that for gamma values that are less than a sixth, we should just defect because the game's not going to last long enough for us to form any kind of coalition. But for things higher than a sixth, a half, 3/4, 0.999, it's going to be better to cooperate than to defect against tit for tat.
Or 6 plus epsilon.
Indeed.
Yeah, I like that. That's actually very cool.
Now, we kind of cheated here because I told you there's just those two strategies, but there's actually a bunch of other strategies you can play against tit for tat. And it's worth thinking through, how do you compute a best response to some finite state strategy? So tit for tat is a finite state strategy, and then it has these these two states, and the strategy is expressed in terms of transitions between those two states. But in general, if we have some kind of finite state strategy like tit for tat, how do we figure out how to maximize our own reward in the face of playing against that strategy? So in this picture here that I drew, the states are labeled with the opponent's choice, the finite state strategy's choice. Okay.
Mm-hmm.
The edges, that's in black. The edges, and labeled in green here, are labeled with our choice. So, for example, if we're in this state, if our opponent is in this state,
Mm-hmm.
we have a choice. We can either cooperate or defect on this round.
Mm-hmm.
So the green arrows tell us how that will impact the state of the opponent. And then these red numbers, I just added the information about, well, I know that if the opponent is about to cooperate and I choose to cooperate, I can just look up in the payoff matrix that that's a -1 for me. All right? Agreed? So I just annotated all these edges, all these choices with these extra numbers. So one of the things that's cool about this is, unlike just the payoff matrix representation that we had before, our choice impacts the payoff, which is the same as that, but it also impacts the future decisions of the opponent. And that gives us this structure here, and also says that this is maybe a little slightly harder thing to figure out because of the fact that we can't just maximize the number. We actually have to think about where that's going to lead us in the future as well.
So 2 things then. One, I was always fond of saying that the matrix was all that you needed, but that really only made sense when you were just playing once.
Yes, that's right.
Right? And 2, I look at this, and it's a finite state machine, but you know what else it looks like to me? It looks like an MDP.
Excellent. It is indeed an MDP. Now, in this case, my opponent's finite state strategy is deterministic, so it's a deterministic MDP. But it's a discounted MDP. Gamma is playing the role of the discount factor. The entries from the payoff matrix are playing the roles of rewards. Our action is playing the choice of our action. And the opponent's internal state structure is playing the role of our states. So it's an MDP. And so how do we figure out what an optimal strategy is against a finite state strategy?
We solved the MDP.
Yeah, exactly. So any method for solving an MDP can then be used to actually compute the strategy. So what is the strategy going to look like? It's going to be a mapping from states of the opponent to action choices for us.
Right. But that's fine because, a state doesn't have to be your state. It's just what matters. So what matters in this case is what the opponent's going to do.
Right. So now what are the strategies that could be meaningful against tit for tat? So we could, if we cooperate, then we're going to stay in this state, and it's always going to be the right thing to do to cooperate. So always cooperate is one. If we defect, now we have a choice again. So we could defect from this state, which would cause us to defect forever. So always defect is another one. But what's the other thing that could happen?
Well, we could tit for tat ourselves.
Well, sorta. So we could defect. So we could defect against cooperate, but cooperate against defect, which would actually cause us to do DC, DC, DC. So those are the only. Oh, I see. No, you're right. I'm not sure how to say it, but the policy is defect when you're in this state and cooperate when you're in this state. But the effect of that is to go back and forth against tit for tat.
Right.
Basically take this loop here. And those are the only policies that matter. And in this case, we worked out that always cooperate is good against tit for tat if it has a high discount factor, and always defect is better if you have a low discount factor. But we can get that for real by actually solving the MDP.
Right, and that makes sense. And the reason those are the only 3, let me see if I get this right. The reason those are the only 3 that make sense is because if you think of this as an MDP, then it has no history. So when you're in C, there's really only 2 choices, and when you're in D, there's only really 2 choices. So if you look at the way you've drawn it, you either stay where you are in C or D, or you take the loop. And those are really the only 3 options, because the rest of them would require you remember what you did, a time step or 2 ago. And there's no way to do that in an MDP, at least not as you've written it.
Well, there's a way to do it. It just would never be better than doing it this way. So an MDP always has a Markov deterministic optimal policy.
Right.
So we only need to consider those.
I think that's the same thing that I was trying to say, but with different words.
Okay. All right, so now that we have a handle on what it means to compute a best response against some finite state strategy, let's actually take a look at these. So this is a quiz. Imagine that we have a gamma that is large, so greater than a sixth.
Mm-hmm.
What is the best response to each of these strategies? So this will be a quiz, but let me just make it clear what the goal of the quiz is. So if you are playing against always cooperate, which of these is the best response to it? Which of these is going to actually have maximum reward? If we're playing against always defect, which is going to have maximum reward? And if we're playing against tit for tat, which are going to have maximum reward? Any questions about that? Does that make sense?
I'm just making certain I have the rows and the columns right. So my opponent is playing on the rows.
Yep.
And so I'm choosing among the columns for each one of those rows. Yes?
Yeah. So I labeled it best possible response for the columns, and these are the opponent strategies on the rows.
Okay.
Okay, go. All right. So is it clear what these answers are?
Let's find out. So let's see. We already worked out the math on this, so we know that for gamma greater than 1/6, cooperating is better than defecting in general. So if I'm going against someone who's always going to cooperate, then I should always cooperate.
Incorrect.
What?
Yes. So we didn't actually work that out. What we worked out was what to do if you're playing against tit for tat. If you're playing against someone who's always cooperating and is completely oblivious to us.
No, you're right. You should always defect because you're always going to win.
Indeed.
Yes,
You're always going to win. You're going to get 0 on every time step.
Right.
Yeah.
No, that makes sense. That's beautiful.
All right. What about always defect?
Well, if you're always going to defect, you might as well defect.
Indeed.
Because we're just in the regular old prisoner's dilemma world.
Good. All right. So now we have this other strange beast here. So our opponent is playing tit for tat. So we could always defect.
Right.
But we get a higher score if we can convince tit for tat to cooperate with us.
For gamma greater than 1/6.
That's right.
So that you should always cooperate.
That is true. However,
Mm-hmm.
what if we play tit for tat against tit for tat?
You'll end up in the same place.
Yeah, so that's just as good.
Mm-hmm.
And that's kind of interesting. If you think about mutual best responses.
Yes.
So that's a strategy a pair of strategies where each is a best response to the other. We have another name for that. Do you remember?
No.
You told us what it was.
Yeah, but I probably use different words.
It's a Nash equilibrium. That's what a Nash equilibrium is. A pair of strategies where each is a best response to the other. There's no way that either would prefer to switch to something else to get higher reward.
And that makes perfect sense. You're in an equilibrium. And it is a Nash equilibrium. Okay.
So we can use this little table here to actually identify Nash equilibrium. So what would a strategy be? So if one player plays always cooperate, then the best response to that is always defect.
Mm-hmm.
But the best response to always defect is always defect. So always cooperate is not part of a Nash equilibrium.
Right.
But what about always defect versus always defect?
No, it is.
So that's a Nash, right?
Yep.
Because they're both doing the thing that is the best response to the other.
Right.
All right, this box here, always cooperate against tit for tat, that's not okay. Because if a player does always cooperate, it's always better to switch to always defect.
Yep.
But check this out. If you are playing tit for tat and the other player is playing tit for tat, there's no reason to switch because it's actually a best response. It's the optimal thing to do. And that works from both players' perspectives.
And that makes sense. So, like you said, check this out, and you've been using check marks. That's very good. So, we're in this situation where we have two Nash equilibria.
Indeed, and one of these Nash equilibria is cooperative, which is the thing that we were sad about, or at least I was feeling really sad about in the last lesson. The idea that, man, it's clear that they should just try to get along. You explained that you can modify the reward structure, and then they would get along better. But here it turns out, well, no, another thing you can do is just open it up to the possibility of playing multiple rounds. As long as you don't know how many rounds, it becomes possible to have a strategy that is best off cooperating and is, in fact, a Nash equilibrium.
Isn't that equivalent to changing the reward structure?
It's definitely related to changing the reward structure. It's a particular way of changing it.
A very particular way.
Yeah, because it's not true anymore that we can do this in the one-shot case. You have to be in the repeated game setting.
Right. So you change your reward structure to be a sum of rewards, but it's actually an expected sum of rewards, and you don't know where it is you're going to stop. So I guess you are change. You change the game. You change the rewards, but in a sort of very subtle way.
Yeah, the whole game is different, really.
Yeah, man, you change the game.
Sometimes you got to change the game. Don't hate the game.
No, you are supposed to hate the game. Don't hate the player. Hate the game.
I'm really proud of us for figuring out a way to make the prisoner's dilemma a little more friendly. It turns out, though, that this idea, this sort of core idea, is very general and kind of cool. So it leads us to a topic that we could call repeated games and the Folk Theorem. So the general idea here is that when you're in the repeated game setting, this possibility of retaliation, the possible of not being cooperative, actually opens the door for cooperation, because now it can become better to just get along and cooperate than to get retaliated against.
Right, and that makes sense so long as the retaliation is plausible.
Well, we're not talking about plausibility of the retaliation. We're just talking about, right, because the tit for tat, it's just not analyzed in that way. It doesn't say whether or not it's actually plausible. It just says, well, if you have this strategy and you play against this strategy, there's no incentive to switch.
Right.
But we'll get into this plausibility thing in a little bit.
Oh, I stumbled across a word. Okay, go.
But I want to point out one thing first, which actually kind of irritates me, kind of along the same lines as like regression is the wrong word and reinforcement is the wrong word. Folk theorem is the wrong word. So what is a folk theorem?
It's two
in
words.
general, in mathematics. Sorry, say again?
A folk theorem is 2 words.
That's fair, yes. So I think it's actually 2 different terms of art. So in mathematics, folk theorems are results that are known, at least to experts in the field, and they're considered to have established status, but they're not really published in their complete form. There isn't some kind of original publication saying, oh, look, I found this thing. It's more something that like kind of everybody knows, and so you don't really give anybody credit for it. So it's like a theorem that is in the general cloud of understanding. It's sort of among the population, among the group.
Wait, does anyone ever prove these folk theorems?
All folk theorems are provable, but it's not like you say that this is Charles Isbell's theorem. It's like, no, it's just a folk theorem. It's like Charles can prove it. We can all prove it, but we're not really sure whoever proved it first. It was just one of those things that everybody knows.
Oh, so it's like an oral tradition.
Yeah. I think that's a good way to think about it.
Okay. I'm just imagining mathematicians sitting around a fire in the winter, cuddled up against one another, sharing theorems that have been proved since the beginning of time to one another.
Exactly. Right. That's the image that I have as well. It's folk theorems. It's the sort of, I learned it from my grandmother and now I'm telling you.
I like that. I like to think of mathematicians that way.
As grandmothers.
Yes.
So that's what a folk theorem is in mathematics. However, in game theory, it means something different. It is referring to a folk theorem, but it's also referring to a particular folk theorem. So the folk theorem in game theory refers to a particular result that describes the set of payoffs that can result from Nash strategies in repeated games. So it's a funny thing. It's a funny way that they use the word. It's a folk theorem, but it's also the folk theorem.
Well, maybe it was actually proven the first time by some guy named Folk.
Oh, that's a good idea. We should push that forward, like call him Folk or something like that. Folk's theorem.
Yeah.
But no.
Oh well, I tried.
Yeah, that's a really great idea that we're gonna just move on from. But what I'd like to do next is kind of build up to this notion of the folk theorem, and it's going to require a couple basic concepts that are not too different from stuff we've already talked about, but we're going to kind of make them concrete, and then we're going to show how they all come together to provide us with this idea of the folk theorem.
Okay.
The thing that I find most useful in trying to understand the folk theorem and what it says and how it works is a thing that I call a two-player plot. I don't know if other people have other names for it, but this concept is out and often discussed. I just don't know what it's called. But here's the idea of it. It's a really simple idea.
It's like a folk plot.
It is a folk plot, right? I don't know who invented this plot. So here's what we're going to do. Remember this Prisoner's Dilemma game. We've got 2 players. There's Smooth and Curly.
Mm-hmm.
And what we're going to do is there's a bunch of joint actions that they can take. So Smooth cooperates and Curly defects, or they both defect, or they both cooperate, or one defects or defect cooperate in the other direction. So what we're going to do is for each of those joint outcomes, each of those joint action choices, I'm going to plot a dot, put a dot on a 2-dimensional plot where this is the Smooth axis and this is the Curly axis. Okay?
Okay.
So cooperate, remember from the prisoner dilemma payoffs, is -1, -1. So I put a dot at -1, -1. Defect is at -6, -6. cooperate defect is at -9, 0, and defect cooperate is at 0, -9. So do those 4 points make sense to you? Do you understand the idea?
They do.
It may not be so obvious why we do it this way, because as you've told us, the matrix is all you need.
Mm-hmm.
But this is really just representing the matrix in another form. But it actually is sort of losing some information, because these dots don't tell us what the relationship is in terms of if one player keeps the same action and the other player changes to a different action. The matrix captures that, but this plot doesn't anymore. It's kind of washed out.
I see.
All right, now, so just to kind of reinforce this idea, and also to let us think about it in a slightly different direction, I want you to consider solving the following quiz. Here's 4 payoffs that I've put little boxes around. This one at -1, -1, this one at -3, 0, and this one at -4, -4. And the question is, which of these payoffs can be the average payoff for some joint strategy? And this is in the repeated game setting.
Okay.
So what we're imagining is these 2 players can coordinate in any way they want. We're not talking about trying to maximize reward or being Nash or anything like that. They're just going to execute some pattern of strategies over infinite run. We're going to average the payoffs that the 2 players get, and we'll say, is it possible for them to adopt a strategy so that the average per time step gets -3 for smooth and 0 for curly? Yes or no? So check that box if that's possible. Can it be that they both get -1 on average? If so, check this box. And can it be that they both get -4 on average? Check this box. Does that make sense?
It does make sense.
All right, so I'll give you a chance to think it through and answer it.
Okay.
All right, so are any of these easy to answer right off the bat?
Well, one of them is really easy to answer right off the bat, and that's -1, -1.
Good.
Because that's one of the points. So if we just
yeah. So the joint strategy to get the -1, -1 would be for both players to cooperate, right? Again, they're just willing to do that just for the sake of showing that they can make that value.
Right. And I think I know the answers for the other ones as well.
All right, hit me.
So here's how I'm gonna talk you through my reasoning, so that at any point I'm wrong, you can gently steer me away from embarrassing myself. Basically, I was looking at these points and I thought, they form a kind of convex hull.
Aha.
And I thought, well, surely that's just an accident of the numbers. And then I thought, oh, wait, of course, we're talking about averages here. So that means that all sort of possibilities have to be inside the convex hull of the outer points. So if I drew a line between those 4 points, I would end up with all possible achievable averages.
Well, achievable averages how? How would you achieve things inside the convex hull?
I would appropriately average them. So in particular, the first thing I noticed that -3, 0 is outside that. So it can't be something you can achieve.
Right. There's no way to make this -3, 0. Certainly not by choosing any of these points, but also no convex combination, no probabilistic combination of them is going to do that either.
Right.
So this one is just right out.
Right. So that leaves -4, -4, and it seems pretty. That's inside the convex hull, so there is some combination of them that would work.
That's right. Any sense of what it would be?
2/3, I think 2/3 DD, 1/3 CC, and I get that by noticing that D comma D is -6, -6, and C comma C is -1, -1, and -4 is 2/3 of the way between there.
Boom. Cool. All right. So you good with that?
I'm good with that. If you're good with that, it's your quiz.
No, I'm excited.
Oh, good.
Yeah. So the -1, -1, and the -4, -4 are doing it. And as you pointed out, there's a more general result here having to do with the convex hull.
Right.
All right. So through the magic of computer graphics, I have a slightly better depiction of this particular region now. As you pointed out, this convex hull of the points is really important, and what it represents is we can call it the feasible region. These are average payoffs of some joint strategy. They may have to collude to do this, and they may not be particularly happy to do that, but the fact of the matter is they can achieve, by working together, payoffs anywhere inside this region.
Huh. So that's what my student Liam always meant when he talked about feasible regions.
Maybe so. I mean, it could be that he meant any of a number of other things, like places that he's willing to live when he goes to get a job.
No, it was all game theory stuff. I just never knew what he was talking about. But now I do, Michael, thanks to you.
Sure. Hey, I'm happy to help. So this is a really useful kind of geometric way of picturing something that would otherwise be a little bit harder to see, I think, in the matrix form.
Sure.
All right, the next concept that we're going to need to understand the Folk theorem is the notion of a min-max profile. So a min-max profile is going to be a pair of payoffs, one for each player, and the value for a player represents the payoffs that that player can achieve by defending itself from a malicious adversary. So what do you suppose a malicious adversary would mean in a game theory context?
Someone who's desperately trying to hurt you.
And what does hurt mean?
Get you the lowest score.
Yeah. And what does that remind you of from your lesson?
My grad students.
You think they're malicious?
It would explain a few things.
Yeah, I don't think they're malicious.
They're sweet.
Yeah, I know a lot of them, and they're wonderful people.
Well, what it reminds me of is they are wonderful people. It reminds me of zero-sum games.
Exactly. So you can imagine thinking about the game that we're playing no longer as being I get my payoff and you get yours, but I get my payoff and you get the negative of my payoff. So you don't really care about yourself anymore. All you care about is hurting me, and that's the idea of a malicious adversary.
I have some ex-girlfriends like that.
It is. People do get into this mode sometimes, and that's actually going to be important in understanding the Folk theorem. So. What I'd like to do is figure out what the min-max profile is for this game. So this is a very famous game theory game example. Sometimes goes by the name Battle of the Sexes.
Is that what the B and the S stand for?
Sometimes it stands for Bach and Stravinsky.
Ugh.
Those are like composers, I think.
You mean like, I don't know, the Backstreet Boys and Sting.
Ah. All right, that works for me. So let me explain this story. It turns out that Smoove and Curly actually got away. They didn't make any kind of deal. They actually just figured out a way of escaping from the jail. So they're back out on the streets again.
Mm-hmm.
And they decided that they'd like to celebrate their freedom by going out to see a concert. And they both decided that in advance, but what they didn't know was which concerts were available. Once they escaped out of the world and couldn't communicate with each other, they discovered that there's in fact 2 concerts in the city that night. The Backstreet Boys are playing, and Sting is playing.
Okay.
Now, as it turns out, each of them is now going to have to choose whether to go to the concert with the Backstreet Boys or Sting, and they're choosing independently. Now, if they end up going to different concerts, they're both going to be unhappy and get zeros.
I see.
If they end up at the same concert, then they're going to be happier. But in fact, as it turns out, Smoove really likes the Backstreet Boys and would prefer that they both end up at the Backstreet Boy concert. But Curly really likes Sting and would prefer that they end up at the Sting concert.
That's not realistic.
Which part?
The fact that I prefer the Backstreet Boys to Sting.
What do you mean you? I mean, this is Smoove. He's a criminal.
That's a fine point that you make there. There is no connection between these characters and ourselves.
Real-life characters, living, dead, or fictional, or mathematical, or instructional.
If so, otherwise purely coincidental.
Yeah, I could switch these around if you'd prefer.
No, I'll go with your fantasy.
All right. I think the payoff matrix might actually look something like we both have 2s in the same place. But anyway, but let's say for the purposes of this example, there's a little bit of a disagreement. Okay, so now what we need to figure out is what the min-max profile is for this game.
Okay.
All right, so that's going to be a pair of numbers.
Mm-hmm.
One number corresponds to the payoff for Curly, and one number corresponds to the payoff for Smoove. And it should be the payoff for Curly should be the payoff that Curly can guarantee himself, even if Smoove is trying to get him to have a low score.
Okay.
And vice versa. Smoove's score is going to be the score that he can guarantee himself, even if Curly is trying to minimize Smoove's score.
All right.
So let's do this as a quiz. So I want you to find the min-max profile for this game, this Bach-Stravinsky game or Backstreet Sting game, and put the number for Curly in the first box and Smoove in the second box.
Okay.
Go. All right, what do you got?
I'm going to say it's 1-1.
All right. How would you figure that out?
Well, first I would ask you if that's correct.
We'll see when you try to figure it out.
Okay. So the idea here is I'm trying to figure out what Curly would get if Smoove was out to make certain that Curly got the worst possible value. So Curly gets to choose among rows, and Smoove gets to choose among columns. So if I chose the B column, then Curly could get a 1. Given a choice, Curly would go for the first row instead of the second row because Curly would get a 1. If I took the S column as Smoove, Smooth took the S column, then Curly would choose the second row and would get 2. And 1 is lower than 2, so Smooth would choose the first column, and Curly would have to get the first row, and it would end up in a 1. Does that make sense?
Yes, but here's what you haven't figured out.
Yes.
What happens if Smooth, because if Smooth says, I'm always going to choose the Backstreet Boys, then you're right, Curly should also choose that and at least coordinate. But what if Smooth is random, say half and half random between the two options?
And I don't know what's going to happen before then?
And you don't know what's going to happen, sorry?
I know it's half, Curly knows it's half and half, but doesn't know which one he's choosing at a given time?
Exactly.
I see. Then I would end up with 1/2 and 1.
Then for choosing B, the expected score would be a half, and for choosing S, the expected score would be 1.
Yep.
Oh, I see. And then Curly would choose S and get the 1.
Right.
And that's still consistent with that.
Mm-hmm.
Can we work out what the worst case is?
What do you mean?
Well, I feel like we should solve it like a zero-sum game, like we did in your lesson.
Oh.
Say that Smooth is actually choosing a probability, either X or 1 minus X.
So I thought you were asking for like a pure decision. I wasn't even thinking about mixed decisions.
Ah, yes. It could be a malicious and randomized adversary.
Ugh. So we really are.
You said ugh.
Well, we really are talking about my ex-girlfriends. Okay, so you just do the math. Do the math.
All right. So if Smooth chooses Backstreet Boys with probability X and Sting with probability 1 minus X, then Curly for choosing Backstreet Boys will get X on average, and for choosing Sting will get 2 times 1 minus X on average. And the useful point is going to be to discover when these are equal to each other.
Yep.
So in fact, Smooth, by being malicious and stochastic, can actually force things down to 2/3. And things being symmetric as they are, Curly can do the same.
Okay.
So basically, Curly can behave in such a way that even against a malicious adversary, he could guarantee himself a score of 2/3.
Yeah, a malicious, possibly mixed adversary.
That's right.
Okay. But 1/1 would be right if we were sticking with pure strategies. But why would we do that?
That's right. But for the purpose, that's right. And you can do a version of the Folk Theorem. In fact, there's lots of different flavors of the Folk Theorem. The one that we're going to focus on is going to allow for these mixed strategies. But in fact, in general, you could say, no, I kind of like the mixed strategies. Let's just stick with that.
No, I like the mixed strategies too. I just wasn't thinking about them.
So I want to point out that, in fact, the solution that you gave, I think that actually does correspond to what is usually called min-max, which is the pure strategy.
Yay!
So the min-max is in fact 1/1. The other concept is really important too, though, and I think it's sometimes called the security level profile. So instead of the min-max profile, the security level profile, and that allows for the possibility of mixed strategies. So that gets you down to the 2/3, 2/3. I think it turns out that there's folk theorems that can be defined with either of those concepts. I prefer this one, but I do like this name better. So I apologize if that made things confusing.
I'm not confused now. I think in the end, Michael, the important thing is we were both right.
Well, the example that I'm going to next, these two concepts line up. So let's do that, and then we don't have to care.
I'm all for that. Let's do that.
So here we are back at the prisoner's dilemma again. You may recall this picture.
Vaguely.
Let's add to this the min-max or security level profile. So for prisoner's dilemma, what is the min-max?
Isn't it D comma D?
It is indeed D comma D, right? So this is the value that you can guarantee yourself against a malicious adversary. Malicious adversary is going to defect on you, and the best thing you can do in that case is to defect yourself.
Yep.
Agreed?
Agreed.
All right, so now let's take a look at the intersection of the following two regions. There's this nice yellow region that we've already got, and then we've got a new region that's defined by this min-max point, this min-max profile. So the region that is above and to the right of this min-max point. So that's the region. This region, all right, we already said that this yellow region is called the feasible region.
Or orange or whatever color it is.
So I'm thinking we can call this other region the acceptable region. And what I mean by that is if you think about it, payoffs in this region are Smooth getting more than what Smooth can guarantee itself in an adversarial situation, and Curly getting more than Curly could guarantee himself in an adversarial situation. So these are all like, better than it could be.
So why not call it the preferable region?
The preferable region. It's preferable to not being in this region.
Mm-hmm.
The intersection of these two
is the feasible, preferable, acceptable region?
Exactly. It's kind of, special from the perspective that it is both feasible and preferable. And now we are ready to state the Folk Theorem. So here's the Folk Theorem. Any feasible payoff profile that strictly dominates the min-max or security level profile can be realized as a Nash equilibrium payoff profile with a sufficiently large discount factor.
Prove it.
What we're going to do is we're going to construct a way of behaving where both players are going to play so that they achieve this feasible profile. And the reason to make that a Nash equilibrium, what we need to do is make it so that it's a best response. And the way that we're going to make it a best response is we're going to say, do what you're told, follow your instructions to achieve that feasible payoff. And if you don't, then the other player is going to attack you. It's going to adopt a strategy that forces you down to your min-max or your security level, and that's your threat. So the best response to that threat is to just go along and do what you're told to achieve that feasible payoff. The only way that that's going to be stable, though, is if the thing that you're asked to do, the feasible payoff, is better than the min-max, right? Because that has to be a threat. You can't threaten somebody and say, do this or I'm going to give you candy. It's got to be do this or I'm going to give you something that's less pleasant than what I've asked you to do.
Okay. That actually makes sense.
Yeah, so this is a really cool idea.
I like it. Hey, could you try saying that again, but with like a southern accent? Just the Folk Theorem part?
Any feasible payoff profile that strictly dominates the min-max security level profile can be realized as a Nash equilibrium payoff profile with sufficiently large discount factor.
I like that because now it's a folksy theorem.
So another way to think about the proof of the Folk Theorem is you could prove it with a little strategy that is referred to as Grim Trigger.
I like that. I like the way it sounds.
So here's the basic structure of Grim Trigger. It says that what we're going to do is we're going to start off taking some kind of action or pattern of actions that's of mutual benefit. And as long as this cooperation continues, this mutual beneficial behavior will continue. But however, if you ever cross the line and fail to cooperate with me, then I will deal out vengeance against you forever.
So once again, we're talking about my ex-girlfriends. I don't know why you're obsessed with this.
Maybe it's just trying to help you understand, so you know kind of what this situation is. Anyway, here's what that looks like in the context of prisoner's dilemma, right? So cooperation is the mutually beneficial action,
Yes.
and as long as you continue to cooperate with me, that's this C arrow here, then I will continue to cooperate with you. But if you ever defect on me, I swear I will spend the rest of my life making you pay. So no matter what you do at this point, defect or cooperate, I will just continue to defect on you. Pain will rain from the sky.
Okay, well, this makes sense. So the idea here is that if you know that I'm going to do this, then hopefully it makes sense for us to continue to mutually benefit.
Right. So the whole purpose of this is to create a Nash equilibrium kind of situation, right? Where if I'm playing this strategy and you're playing this strategy, then neither of us has any incentive to cross the line, and so we're just going to continue to cooperate. Crossing the line is going to decrease your reward, so there's no benefit to doing it, so you won't do it. So
Right.
it's nice because it gets us a Nash equilibrium.
Hmm.
But there's a problem with it.
Of course.
And you pointed it out before, so let's dive in and make sure that we understand it and see if we can fix it.
Okay.
The problem is that in some sense, the threat is implausible. And in a very kind of real sense. So what's happened is if you do fink out on me, if you do cross that line, the idea that I will then spend the rest of my days punishing you, foregoing reward myself, right, not taking a best response against you, seems kind of crazy. Do you agree?
Yeah, again, my ex-girlfriends. Yeah, I totally get this.
No, I'm saying that nobody would do that.
Right. So it would be like being in an elevator with a stick of dynamite and seeing that someone has $100 and saying, give me your $100 or I'll blow us both up. That's not really a reasonable threat because the alternative to me not giving you $100 is you die, which seems probably not worth it.
That's right. So you can think about the possibility of, okay, I'm going to not give you the $100. You say that you're going to blow me up, but you will hurt yourself more than you hurt me, so it won't be a best response. Not blowing me up and just not getting the $100 and leaving the elevator is better for you than blowing me up.
Right.
So that is an implausible threat. So the way that we formalize this idea in the game theoretic context is to say that we're interested, a plausible threat corresponds to something that's called a subgame perfect equilibrium.
Okay.
So subgame perfect means that each player is always taking a best response independent of the history. All right, so let's actually look at a concrete example here. Let's imagine playing Grim Trigger against Tit for Tat. So my first question to you is, are these two strategies in Nash equilibria with each other?
Yeah, I guess so.
And why is that?
Because the fact, if one player is playing tit for tat, then the Grim Trigger thing doesn't matter anyway, because both of you are going to cooperate forever, and it doesn't make any sense to deviate.
Right, so any strategy that I could choose that's different than Grim Trigger is going to, on average, do no better, possibly worse.
Right.
So I might as well stick with Grim Trigger. And Tit for Tat has the same kind of feeling about it, that it's cooperating with Grim, and it can't really do anything better, so it might as well do that.
Right.
So the next question to ask is, are these two strategies in a subgame perfect equilibrium with each other? And the way that you actually test that is you say, well, they are not subgame perfect if there's some history of actions that we could feed to these machines, so that here's what Grim is doing. It's some sequence of cooperates and defects, and here's what Tit for Tat is doing. It's some sequence of cooperates and defects. And once we've reached some particular point, is it the case that one or the other of these machines is not taking a best response, that it could actually change its behavior away from what the machine says and do better than what the machine says? If that's the case, then it's not subgame perfect. But if it's the case for all histories, they're always taking a best response, then it is subgame perfect. So do you see a sequence of moves that these two players can take where one or the other of them is not going to be doing a best response?
It's can take, right? As opposed to will take.
I don't understand.
Yeah, I'm not sure I do either, which is why I asked the question. It's not a made-up history. It's like an actual set of moves that are consistent with Grim and Tit for Tat?
No. So it is not necessarily. So we know that if we actually play these against each other, the only history that we're going to see is
cooperative forever.
Right. Grim is going to do cooperate. Tit for Tat is going to do cooperate.
Right.
And so they are, and everything's fine. The question is, can we actually go in and alter the history so that one or the other in the machines could take a better action than the one that the machine tells it to take?
Yeah, if Tit for Tat ever does a defect.
All right, so let's take a look at that. So let's say on the first move, Grim cooperates and Tit for Tat defects. Okay, so let's say that that's the moment in time. What will the machines do at this point?
Well, at this point, the next time step, Tit for Tat will cooperate and Grim will defect.
Good, and then thereafter?
Grim will always defect.
And then Tit for Tat will always defect.
Right.
So the payoff that Grim gets at this point is going to be, well, initially high, but then very, very low. On the other hand, could Grim have changed its behavior to do better than this?
Yeah, just by doing, just by choosing to cooperate.
By choosing to cooperate. So sort of ignore the fact that Tit for Tat did the defect and instead do a cooperate here, then Grim would do better. So the idea is that Grim is making a threat, but when it comes time to actually follow through on that threat, it's actually doing something that is worse for itself than what it would do otherwise. Do you see that?
I do.
So is it subgame perfect? No. And the proof of that is exactly what you said. Take a look at this history. Here's a history where Grim would not be willing to actually follow through on its threat.
Right.
So it's an implausible threat, and that's bad. So maybe we've now just undone all the awesomeness that we had done.
No.
Well, maybe. I mean, the awesomeness was, hey, look, we can actually get machines that are in Nash equilibrium, and they're cooperative in Prisoner's Dilemma, so they're actually kind of doing the right thing. And it turns out, well, they are, but they're depending on this notion of implausible threats to do it.
How should I feel about that?
Well, let's see if we can fix it.
Okay.
All right, so let's make sure that we get this concept. So let's evaluate tit for tat versus tit for tat, spy versus spy, and ask whether or not they are subgame perfect or in a subgame perfect equilibrium with each other. And your choices are yes and no. But if you say no, I'd like you to give me a sequence to show that it is not subgame perfect. In other words, that if they were to take this sequence of actions, and this one was to take this sequence of actions, it would leave the machines in a position where they would not be willing to follow through on their threat, that it would be better for them to do something else in the long run, assuming that they're still playing against the other tit for tat machine.
From that point on.
Yep.
Just imagine that someone could go in and change one thing. Would you still want to follow tit for tat the next time step or not?
Yeah, I don't know that it has to be just one thing, but yeah, that's right. Change the sequence leading up to this point and then say, okay, do you still want to do what tit for tat is telling you to do, or would you rather do something else?
Right. Okay, I think I got it.
Cool. All right. Go. Okay, what's your answer?
My answer is no.
No, I'm sorry, that's wrong. No, I think that, well, if it's right, then we need to provide a sequence that proves it.
Okay.
So what are you thinking?
Well, I was thinking actually something very similar to what we just saw.
Okay.
So tit for tat, what they're going to do is they're going to do cooperate, right? That's what they normally want to do.
Exactly.
So what would happen if at one point one of them defected?
Okay, just for simplicity, let's make it the very first point.
Mm-hmm.
So tit for tat number 1 defects, and tit for tat number 2 also defects?
At the very first time, no, it cooperates because it's done at the same time.
Well, I mean, so we can feed it anything we want. So we could tell tit for tat 2 to cooperate. It's sort of like we've taken over its brain for a brief amount of time.
So I'm not yet convinced it's going to matter for this. But the thing is that from that point on, tit for tat 2 is going to want to, for the next step, tit for tat 2 is going to want to defect.
That's right.
And tit for tat 1 would want to cooperate.
Uh-huh.
And that sort of sucks for tit for tat 2, right?
So, I don't know. So maybe we should try to think through what is the expected reward for tit for tat 2 to actually do this defect at this time. Or wait, no, so sorry, to stick with the tit for tat machine at this time.
Well, what's going to happen at that point is it's going to keep alternating.
That's exactly right. So it's going to get the rewards corresponding to D versus C, C versus D, D versus C, C versus D.
Over and over again.
Yeah. So let's think about in the average reward case. So in the D versus C, if it does D when the other machine does C, then it gets 0.
Mm-hmm.
If it does C when the other one does D, it gets -9.
Mm-hmm.
And then this alternates.
Yep.
So if we look at the average reward, which is basically what you get when the discount factor is very, very high,
Mm-hmm.
it's scoring -4.5.
Right.
Is there any way that it could behave against tit for tat, starting from this point, that would do better than -4.5?
Just go ahead and cooperate.
Just cooperate forever.
Well, cooperate the next time, and then keep doing tit for tat from that point on. It'll work out to be cooperate forever.
On average, that's right, which will get us a -1. So not being tit for tat at that point, but instead turning to always cooperate would actually get it better. So the idea that it should defect at this point is an implausible threat.
Exactly.
So this is not subgame perfect. So yes, you nailed it.
Yay.
Does that make sense?
It did make sense.
Good. All right. So that leaves open the question of, is there a way to be subgame perfect in Prisoner's Dilemma?
Can I ask you a question?
Sure.
Before you answer that? So I had sort of convinced myself that it didn't matter whether tit for tat number 2 started out with C or started out with D. I'm trying to decide whether that's actually true.
Okay, that's a good question. So what will happen from this point on, if we now continue, we took over the brains of tit for tat and we forced them to play defect against defect. And now we release that and we let them do whatever it is that they're going to do. And what are they going to do is
They would
defect
defect
forever.
Yeah.
And is there anything that tit for tat 2 machine could do to get a better score than that?
Cooperate.
Yeah, so it could cooperating with tit for tat. We'll bring it back into mutual cooperation. It will actually get a better score.
Yeah.
So in one case, it would average to -1, and the other one it would average to -3, and -1 is better. So you're right. Good point.
Okay.
So really, what matters is that we get them defecting.
Right. Okay, so that makes sense. So I was right that it didn't matter, although you do get slightly different answers or slightly different averages.
That's right. But in both cases, there's a way of getting a higher average.
Right. Okay, cool. That's what I thought. I thought it was something like that. So now let's go back to what you wanted to do. So are we going to be able to figure out how to do Prisoner's Dilemma in a way that is subgame perfect?
Well, how about I propose a machine and we'll see what it does.
Okay.
So here's a machine that is sometimes referred to as Pavlov, named after the Russian psychologist who was studying gastric juices and then figured out how animals learn. So I don't know why it's called that in this particular case. But here's what the machine looks like. It says start off cooperating, and as long as the opponent keeps cooperating, then cooperate. So far it sounds a lot like tit for tat.
Yeah.
If you defect, then move to the defect state. So Okay, it still looks a lot like tit for tat. And again, this defect state has two arrows coming out of it, but they're reversed from what they were in tit for tat. Here it says, if you cooperate with me, I will continue to defect against you. But if you defect against me, then I'm willing to cooperate with you. So that's a little strange, right?
That is a little strange, yes.
So, the way to get me to stop defecting against you is to defect against me. And then I become cooperative again.
So in other words, take advantage of you until you sort of pull a trigger on me.
Seems like it.
Yeah.
It's a funny thing. So again, tit for tat is like repeat what the opponent did. Pavlov is basically cooperate as long as we're agreeing. If we both defect, I'll cooperate. If we both cooperate, I'll cooperate. But if we disagree, if I defect and you cooperate, or you cooperate and I defect, then I will defect against you on the next round.
That sort of makes sense.
Really?
Yeah, right? I mean, it says if you're cooperating, I'm going to cooperate. If we're going to both start out cooperating, and then if you ever defect on me, then you have basically attacked me, and so I'm going to defect on you unless you start cooperating again, in which case I think that you're being reasonable because of what I did, and so now we're going to start cooperating again.
Except that's tit for tat.
No, you're right. You're right. I take it back. It doesn't make any sense.
Yeah, it's weird. It's
a
little bit weird.
Too many V's.
Too many V's?
Mm-hmm.
In Pavlov,
yes.
The two V's. Yeah, but you can think of them as being like arrowheads.
Oh, well, then that makes much more sense.
Yeah, exactly.
Okay.
Yeah, so it's this weird thing where I'm going to continue to defect against you until you realize that I'm hurting you. You punch me once, and now, okay, good, we're even again. We good? Yeah, we're good.
Oh, this is like men on a basketball court.
Yeah, sure. But now here's the question. Is this Nash? So we'll make that a quiz. So here's a quiz, and I chose it this way so I can maximize the number of V's in one sentence. Is Pavlov v. Pavlov Nash?
I think I know the answer.
All right, let's give everybody else a chance to think about it.
Okay, go.
All right, what do you get?
I say yes.
And the answer, that comes from what?
Well, you both start off and cooperate, and so you're always going to cooperate, and it doesn't make any sense for anyone to ever move away from cooperation.
Indeed.
Hence, you're in equilibrium. In particular, you're in a Nash equilibrium.
That is correct. So that's very good. So you were able to realize that Pavlov is a Nash equilibrium, but we can go further than that, or farther than that.
Further.
We can go further than that and show that, in fact, Pavlov is subgame perfect. So unlike tit for tat, it's actually subgame perfect. So let's take a look at how we could convince ourselves of that. So I think the important thing to see is that by feeding these two Pavlov machines different sequences, we can get into any of these four different combinations of states. They're both in the cooperation state. They're both in the defect state. One's cooperate, one's defect, and one's cooperate.
Mm-hmm.
And so is it the case that no matter which state those are in, that the average reward is going to be mutual cooperation? So let's check. So if they're both cooperating, and then we continue with these Pavlov machines, then they will mutually cooperate. So yes. All right. If we're in defect, then what's going to happen?
Well, then they both agree, so they cooperate.
So they're going to move to cooperate, and then they'll stay there forever. So then that'll be mutual cooperation. Awesome. What if one's in cooperate and one's in defect?
Then they disagree.
Right.
And they move to the other state.
More specifically, what?
Oh, I don't know. I can't remember. I'm trying to keep track of who's who. So if I cooperate and you defect, then let's see. The guy who cooperates moves to defect, and the guy who defects moves to defect. Because now you agree, and so you're going to cooperate.
Boom. So when we're in the cooperate defect state, then on the first move, let's see, the right hand Pavlov just defected, so that causes this transition, and this guy just cooperated, which causes this transition, so that we've gone to defect.
Right.
Which means that we're going to average cooperation, because that's where we're going to get stuck in the long run.
Right.
And the same thing works through here. Boom.
That's actually very cool and kind of counterintuitive.
Yeah. It's really neat. So sort of no matter what weird sequence we've been fed, we manage to resynchronize and then return to a mutually cooperative state.
So I have a question for you.
Go for it.
So presumably this is really cool, like mathematically, because now we should all be Pavlovians, like we're all Keynesians, and then we just kind of move forward from there. Do people do this?
I don't know the answer to that question.
I mean, other than men on a basketball court.
Sure, you can always return to that. Though I'm not sure I'm aware of any analyses of men on a basketball court and whether or not you know people have analyzed that.
Hmm.
But how about this? If I find out, I will post something on the instructor comments.
Okay, that sounds reasonable. So Pavlov is subgame perfect. That's awesome. So remind me again why I care that something's subgame perfect.
Because it means that, so let's say that you actually, so I'm being this left Pavlov, and you defect on me, and you're like, yeah, I'm going to defect on you because I just want to take advantage of you, because you're gonna forgive me, and I will have gotten this extra bonus for that. And what it turns out is that, no, if we do Pavlov against Pavlov, we're going to fall into mutual cooperation no matter what. So this defection that I do, this threat, this punishment that I deal out to you, you can earn it back, and we can go back into a cooperative state.
Right.
So it's worth it to me to punish you because I know that it's not going to cost me anything in the long run, and it stabilizes your behavior in the short run.
Sure, makes perfect sense.
So it becomes a plausible threat.
I like it.
So this Pavlov idea actually is more general than just the prisoner's dilemma or iterated prisoner's dilemma, and in fact led to a result that I like to call the computational Folk Theorem. The idea of the computational Folk Theorem says that you give me any two-player bimatrix game.
What's a bimatrix game?
Just that there's two players.
Okay.
So it seems kind of redundant, doesn't it?
It does.
What makes it bimatrix, as opposed to a two-player zero-sum game, which you can write down with a single matrix, this is like each player has its own reward matrix.
I see.
But you're right. I could have just said bimatrix game and left out the two-player. And it's an average reward repeated game. So we're going to play round after round after round, and we're going to look at the average reward. Or you can also think of it as discounted with an extremely high discount factor.
Okay.
So you give me one of those games, and what I can do is I can build a Pavlov-like machine for any of these games and use that to construct a subgame perfect Nash equilibrium for any of these games in polynomial time. Wow. So, and the way that this works is, if it is possible for us to have some kind of mutually beneficial relationship, then I can build a Pavlov-like machine quickly. If not, then the game is actually zero-sum-like, right? Because in a zero-sum game, we can't mutually benefit, so we can't do anything like Pavlov. We're just going to beat each other up. So we can actually solve a linear program in polynomial time and work out what the strategies would be if we're playing a zero-sum-like game. And so either that works and produces a Nash equilibrium, and we can test that, or it doesn't work, but at most one player can improve its behavior. And by taking that best response against what the other player does in a zero-sum-like sense, then that will be a Nash equilibrium. So there's three possible forms of the Nash equilibrium, but we can tick through these, figure out which one is right, and derive the actual strategies in polynomial time.
Wow, that's pretty impressive. Who came up with this idea?
So this is a result due to Peter Stone and somebody. Me.
Ah. Well, that's very impressive. So you managed to find a way to sneak in some of your own work into this class.
Here, let's do some more of that.
Okay. I'm a big fan. And I think that's fair because I did that way back when on Mimic.
Mimic. So, yeah, so the last topic, that's all I really wanted to say about the Folk Theorem and repeated games. What I'd like to do now is move to stochastic games, which is a generalization of repeated games, and talk a little bit about how this relates back to things like Q-learning and MDPs.
Oh, okay. That sounds good. Almost sounds like you're wrapping up.
It is that, and that will be the end of the new material.
Wow. But that means we're coming towards the end of the entire course.
I know. We're going to all cry with disappointment. And I think, and I just say this, as an idle suggestion, that the students should demand that we teach more classes.
I concur. So let's get there so that they can demand.
So what I'd like to tell you about is a generalization of both MDPs and repeated games that goes by the name stochastic games, also sometimes Markov games. I like the name Markov game better, but I use stochastic games because that's what other people call it, and sometimes it's good to use words that other people use. And what stochastic games give us is a formal model for multi-agent reinforcement learning. In fact, I like to think of this in terms of an analogy, which is something like MDP is to RL as stochastic game is to multi-agent RL. It's a formal model that lets us express the sorts of problems that take place in this formalized problem setting.
That sounds very promising.
Cool. All right. So let me give you. I'll start off by explaining it in terms of an example, and then I'll give a more formal definition because I can't not. So this is a little game played between A and B. Oh, I should have it between Smooth and Curly, but traditionally it is played between A and B.
And sometimes it's good to use the words that other people use.
I've heard that, but I wouldn't say it quite that way. So this is a 3x3 grid. Each of the players can go north, south, east, and west, and can stay put if that's helpful. And the transitions are deterministic, except for through these walls here, which are called semi-walls. So these thick lines represent walls that you can't go through. The thin lines just represent cell boundaries. But this kind of dashed line here is a semi-wall, and that means if you try to go through that, say by going north if A goes north from this position, then 50% probability A will actually go to the next state, and 50% probability A will stay where A is. So the goal is to get to the $sign, and if you get to the $sign, you get $100. So if we ignore A for a second, what should B do to minimize the number of steps necessary to get the reward?
Go left and then go up, then go up. Or I'm sorry, go west and then go north and then go north.
Yeah. And what should A do, ignoring B?
Go east and then go north and then north.
Yeah. Unfortunately, these guys live in the world together, and what happens is they can't occupy the same square, and as soon as somebody reaches the $sign, the game ends, and the other player, if the other player hasn't reached the $sign, gets nothing.
I see.
So now there's a little bit of contention.
So what happens if A and B both try to go to the same square at the same time?
Let's say that we flip a coin and one of them gets to go first, and then the other one will bounce off of the first one.
But that's not a problem when it comes to reaching the money.
But it's not a problem. Yes, right. So the money is kind of like a money pit.
I don't think that's what a money pit is, but okay.
And so they can dive in and they both get the money because they're in the money pit.
I like it.
So what do you do if you're A? How do you play this game? Oh, let's think of another thing. Can you think of what it might mean to have a Nash equilibrium in a game like this?
Oh, that's an interesting question. It would mean, what do you mean, what would it mean? It would mean that neither one of them would want to deviate.
It would mean a pair of strategies for the two players. Now, the strategies are now multi-step things that say, they're like policies, right? So it's a pair of policies such that neither would prefer to switch. So can you think of a pair of policies that would have that property?
Well, no, I'm not sure. I was trying to think about that. So I was thinking that kind of, if I were a nice guy, what I'd want to do is I'd want us both to try to go through the semi-walls, and if we both go through the semi-walls, we just go up again, and then we hit the $sign at the same time, and that's very nice.
So, okay, good. So that seems like a cooperative kind of strategy, right, where they're both, 25% of the time, both will get through, both will go to the goal together, hooray, but
25% of the time, neither one will get through, and then we're in the same place we were before, so that's okay. The problem is the other 50% where one of them gets through and the other doesn't.
Right. So what do you do if you make it through and the other one doesn't?
What do I do if I get through and the other one doesn't? Well, if I'm only going to do this the one time, then I just keep going and get the $, and the other person loses.
Yeah. All right. So what this works out to be is that A is going to get to the goal 2/3 of the time, and B is going to get to the goal 2/3 of the time.
Mm-hmm.
So, all right. So if that's the case, if I say, okay, A, that's what you should do, B, that's what you should do, then is there a way that either A or B can switch strategies and do better?
Well, if B, for example, decides to go west and then go up, what happens?
Yes, that's a good question. B will now make it to the goal 100% of the time, and A will only make it to the goal 50% of the time. So B has an incentive to switch to this strategy if we tell them to both go through the semi-wall.
Right.
So that wasn't a Nash equilibrium. B would want to switch to this new policy.
Mm-hmm.
Is this a Nash equilibrium?
No. Wait, is it? No. Because why doesn't A just choose to go east?
Well, would A do better on average by switching to this strategy?
Well, let's see. No, actually. Oh, no, you said half the time they go through.
Yeah.
So half the time you flip a coin. So half the time I don't make it.
Right.
But half the time I do. So actually it looks the same.
It looks the same. That's right.
And B would go from 1 to 1/2.
Yeah, that's true. So A doesn't have an incentive to do it, but B is hoping very much that A doesn't do that.
Right.
So there's one Nash equilibrium where B takes the center, another one where A takes the center. I guess if we do this coin flip thing, it works out this way. If it's the case that if they both if we change the rules here so that if they collide, neither of them gets to go, then both trying to go to the center is not a Nash equilibrium anymore because you can do better by actually going up the semi-wall.
Right. And so if collision means nobody goes through, then suddenly you would want to do the other thing, where one of you goes through the semi-wall and one goes the direct way.
Right. So we can see that there's a bunch of different Nash equilibria here, and that it's not so obvious how you'd find them, but it is at least clear that they exist and they have a different form than what we had before because now they're policies instead of these otherwise simplified choose this row of the matrix.
Mm-hmm.
Cool. All right, so let's think about how we might learn in these kinds of environments.
Oh, okay. I like that already.
So stochastic games, originally due to Shapley, have a bunch of different quantities: states, actions, transitions, rewards, and discount factors. And here's how we're going to do it. We're going to say that little s is one of the states, and actions could be like little a, but actually, since we're going to focus mostly on two-player games for the moment, I'm going to write actions as A and B, where A is an action for player 1 and B is an action for player 2. Sound okay?
Sure.
All right, so next we have the transition function. So the transition function says if you're in some state S and there's some joint action that's taken, like all the players choose their action simultaneously, A, B, then what's the probability of reaching some next state S prime? And we can write rewards the same way. So there's reward for player 1, given that we're in state S and there's a joint action AB, and there's the reward for the other player, second player. And the discount factor is, like a discount factor.
Sure, that makes sense. So, it's the same discount factor for everyone.
Yes, good point. One need not define things that way, but in fact, that's the way it's always defined.
Hey, not to go off on a tangent here, but sometimes I see MDPs and things like stochastic games defined with the discount factor being a part of the definition and sometimes not. Like it's just a part of the definition of the problem, or sometimes it's a parameter of an algorithm. Which do you prefer? Why have the discount factor actually listed as part of the definition of the game?
I have no justification other than it's nice to have listed the things that might be important, as opposed to working through algorithms for a while and then saying, oh yeah, there's this other number that kind of matters too.
Okay, that's fair. I was just curious.
So one of the things that I actually find really interesting is that this model was laid out by Shapley, one of the a former Nobel Prize winner. I guess once you're a Nobel Prize winner, you're a Nobel Prize winner forever.
Yeah,
so
stop being former.
Shapley, the Nobel Prize winner. And as we're going to see in a moment, this model is actually a generalization of MDPs, but Shapley published it before Bellman published about MDPs.
Oh, this is pre-Bellman.
So MDPs, to some extent, can be thought of as a narrowing of the definition of a stochastic game.
Huh.
So, all right, let's do a little quiz and see that we really understand the relationship between this model and other things that we've talked about.
Okay.
All right, so stochastic games are more general than other models that we've talked about. And so just to make that case, here's a way of making the stochastic game settings more constrained, and by making them more constrained, actually turning them into other models that we've talked about or could talk about. So I wrote down 3 different ways of constraining the stochastic game model. One says that we're going to make the reward function for one player the opposite of the reward function for the other. The next one says that the transition function has the property that for any state and joint action and next state, that's going to be equal to the transition probability for state, joint action, next state, where we've changed potentially the choice of action for player 2.
Mm-hmm.
So basically, player 2 doesn't matter to the transitions or the rewards for player 1, and the rewards for player 2 are always 0. So that's again, you can specify this as a stochastic game. And then in the third case, we are saying that the number of states in the environment is exactly 1.
Mm.
So I claim that by doing these restrictions, we get out the Markov decision process model, a zero-sum stochastic game model, and the repeated game model that we've been talking about in the context of like the Folk Theorem. So what I'd like you to do is write the letters A, B, and C in the correct boxes.
Okay.
Go. All right. Talk me through it.
Okay, so I'm going to say that I think I know the answers for this one. And let's start with the first one. So R1 equals minus R2, which you'll notice they are equal and opposite. And in fact, if you add them up, that is, you sum them, you end up with 0. So I'm going to say that's a zero-sum stochastic game.
Nice.
For 2, basically you're saying that for all intents and purposes, there's only one agent, which just makes it a regular Markov decision process.
Yeah. So isn't that interesting that that just by making the other player irrelevant, then that's what an MDP is. It's like a game where the other players are irrelevant.
Yeah, which both of my children are like that. But okay, I think that's pretty cool. And in fact, I'd be right in saying that R2 doesn't have to equal to 0, as long as it just equals to some constant.
Yeah, constant. Actually, depending on how you think about it, it could be, we could just ignore the whole R2 thing and just say that as far as the first player is concerned, since the second player really has no impact on anything, it doesn't matter. But the reason I put that in is I got kind of scared that, like, I feel like if I lived my life and knew that my actions affected the state and my rewards, but they were also affecting the rewards of somebody who didn't matter, like, I feel like that would actually still have an influence on me.
Sure, but then the way you'd get around that is you would say, well, your R1 is actually equal to your R2.
Oh, so if I had gone like that, wouldn't that be the case then that we're saying? Oh yeah, I see that the second player is irrelevant, but the first player may be relevant to both.
Right.
Yeah, okay, I like that a little bit better.
Yeah, I mean, once again, it all boils down to changing the rewards. Okay, and so given A and B, I know the answer to 3 must be C, unless you're tricking me, and it could be A or B again, which I suppose you could have done. You didn't say they were mutually exclusive. So let me actually argue why it would be C. Well, there's only one state, and since you're in a stochastic game and you're going to be continually doing this, it means that you're basically doing the same game over and over and again. So it's a repeated game.
Yeah. So in particular, the actions impact the rewards, but they're not going to impact the transitions because you're always just going to go back to where you were. The discount factor plays the role of deciding when the game is going to end stochastically.
Mm-hmm.
And so, yeah, it's exactly a repeated game. Like, this is the one I feel most comfortable about because this really does recover that same model that we've been talking about.
I like it.
Cool. Now, given that we actually are now in a model that generalizes MDPs, it would be nice if we could generalize some of the things that we did with MDPs, like Q-learning and value iteration, to this more general setting. So that's what we're going to try next.
Cool.
Now, what makes stochastic games more interesting, perhaps, than repeated games is the idea that the actions that the players take impact not just the rewards, but also future states. Right. So this is the same issue that comes up when we're talking about Markov decision processes. And the way we dealt with it in that setting was by defining a value function. So it seems pretty reasonable to try to go after that same idea again. So what I've got here is actually the Bellman equation. And let's look at this together and see if we can fix it because it's not quite right for dealing with the idea of zero-sum stochastic games. So, okay, so you remember the Bellman equation? We've got Qi star.
Mm-hmm.
So there was no I before, but Q star is the state. It's defined over state actions. So here we're going to define it over joint actions for the two players, action pairs. The immediate reward to player I for that joint action in that state, plus the discounted expected value of the next state. So we need to factor in the transition probabilities. So the transition of actually going to some next state S prime is T of S, AB, S prime, right? So now we're imagining what happens when we land in S prime. So what I've written here says, well, we're going to basically look at the Q values in the state that we landed in and kind of summarize that value back up so that we can use it to define the value of the state that we left. You with me?
I am with you.
All right, so if we put this in, if we say the way we're going to summarize the value for this new state that we land in is we think of it as actually a matrix game, right? That there's payoffs for each action choices of A prime and B prime. And over all of those, we need to kind of summarize, well, which of those actions in this table of values that we get for S prime, which of those values are we going to propagate forward and call the value of that state? So what we did in regular MDPs is we said, we'll just take a max over all the actions, or in this case, all the joint actions.
Mm-hmm.
So what do you think that translates to?
Well, you wrote down max, but that doesn't make sense. That can't be right.
Well, it means something. It just doesn't mean what we mean it to mean.
Ah, that's true. That's fair.
So what does it mean, and then how can we fix it? So let's start off with what does it mean?
It means that you kind of always assume that the joint actions that are going to be taken will benefit you the most. So everyone is trying to make you happy. So this makes you optimistic?
Yeah, it's sort of optimistic to the point of
Delusion?
yes, very good. Right? It just basically says whenever we're in a state, the whole world is going to choose their actions to benefit me. And this is not what we get in, say, a zero-sum stochastic game. In a zero-sum stochastic game, we should be, like fighting it out at this point.
So that would work out if everybody's rewards were the same, or everybody's rewards were the sum of everyone's rewards, or something like that.
That's right. If it was some kind of team-based game, or if everybody, was going to sacrifice their own happiness for the benefit of QI, or I mean. So it's not reasonable to assume that. In fact, what was it that we were assuming when we had a zero-sum game that was just a single stage, right? Just a single game, and then we were done.
Oh, that people were doing Minimax.
Right.
And Maximin.
So what if we change the equation to look like that? So what I mean by this is when we evaluate the value of a state, we actually solve the zero-sum game in the Q values and take that value and use it in the context of this equation.
That seems closer to right.
Yeah. I mean, it's not an unreasonable thing to do. It's just to say, I'm going to summarize the future by imagining that we're going to play that game that represents, all the future.
Sure.
And I'm going to act in such a way to try to maximize that, assuming that you're trying to minimize it, which makes perfect sense if it's a zero-sum game.
Right. And we're still acting as if there are only two people here.
Yeah, that's right. It turns out that when you're talking about zero-sum, it really implies that there's only two players. Because if you have a zero-sum three-player game, it really is just a general-sum game. You can imagine that the third player is just an extra factor that's just messing with the numbers to make things sum up to zero. So, so zero-sum really does kind of focus on this two-player setting.
That makes sense.
So we've got this modified Bellman equation, and we can even translate it into a form that's like Q-learning. So the analog of the Bellman equation and the Q-learning update in this setting would be that if we're in some state, there's some join action that's taken, there's some pair of rewards that comes, and some next state that's visited, that the Q value for that state join action pair is going to be updated to be closer to the reward for player I plus the discounted expected value, the discounted summarized value or V value of the new state S prime, and we'll use Minimax to summarize what the values are in that new state.
I like it.
And that equation is sometimes referred to as Minimax Q, because it's like the Q-learning update, but just with the Minimax operator instead of a max.
That makes sense.
So if we set things up this way, we actually get some wonderful properties coming out. So here's some things that we know about this setup for zero-sum stochastic games. Value iteration works. So we can actually solve this system of equations by using the value iteration trick, which is to say, we initialize these Q values to whatever, and then we just iterate this as an assignment, right? We just say, equals. So value iteration works. This Minimax Q algorithm converges under the same kinds of conditions that Q-learning converges. So we get this nice, Q-learning analog in this multi-agent setting. The Q star that's defined by these equations is unique. So we iterate it and we find it, and there's just that one answer. The policies for the two players can be computed independently. That is to say, if two different players are running Minimax Q on their own and not really coordinating with each other except for by playing the game, that the policies that they get out will actually converge to Minimax optimal policies. So it really does solve the zero-sum game, which is maybe not so surprising because, they are trying to kill each other after all. So the idea that they'd have to collaborate to do that efficiently would be weird.
I never thought about it like that, but yeah, that would be weird.
This update that I've written here can be computed efficiently, which is to say in polynomial time, because this Minimax can be computed using linear programming.
Yes, of course.
And finally, if we actually iterate this Q equation and it's converging to Q star, knowing Q star is enough to figure out how to behave optimally. So we can convert these Q values into an actual behavior, again, by using the solution in the linear program.
So it's just like MDPs and value iteration with Q-learning.
Exactly. It's like we've gone to a second agent, and it really hasn't impacted things negatively at all. This is all pretty much all the things that we want come out. There are some things that don't come out. For example, in the case of an MDP, we can solve this system of linear equations in polynomial time, not just by value iteration, but we can actually set it up as a single linear program and solve it and be done in linear time. Or sorry, not linear time, polynomial time. This is not known to be true in the zero-sum stochastic game case. It's not known whether it can be solved in polynomial time. So it is a little harder as a problem, but it's not harder, not deeply harder, and not harder in a way that matters in a machine learning setting.
Cool.
So this is really great. So let's try to take this same approach and see if we can deal with general sum games.
Okay.
So let's think about general sum games. So not zero sum anymore, but we're not restricted. It could be any kind of relationship between the two players. Okay. So the first thing we need to do is realize, well, we can't really do minimax here anymore, right? Because that doesn't make sense.
Right. That only works with zero-sum games.
Well, it's only it sort of assumes that the other player is trying to minimize my reward, and that's not the concept of a Nash equilibrium. We'd like to do something analogous and find a Nash equilibrium in this general sum setting. So
okay.
what operator do you think we would need in this context here?
Nash equilibrium?
Yeah. So that would be a very reasonable thing to do. Is instead of computing minimax, we actually compute of the two matrix game, right, using Q1 and Q2, compute the Nash equilibrium of that and propagate that value back. It's a well-defined notion, right, that we can summarize the value of these two payoff matrices with a pair of numbers, which are the values of the Nash equilibrium.
Mm-hmm.
All right. So good. So we can do the same thing in the Q-learning setting, substitute in a Nash equilibrium, and we can call that algorithm Nash Q, which appears in the literature.
Nice.
Oh, Minimax Q, by the way, is something that I wrote about. Nash Q is a different algorithm.
So it's not as cool, is what you're saying.
Well, let's see how it goes. So this is now an algorithm. You can actually, this is a set of equations. It's not really clear exactly what it means, but we can think about turning that into value iteration, right? By turning this into an assignment statement.
Mm-hmm.
So what happens? Well, value iteration doesn't work.
No.
So if you repeat this over and over again, weird things can happen. It doesn't really converge. It doesn't really solve this system of equations necessarily. And unfortunately, the reasoning here is even harder in the case of Nash Q, because in the case of Nash Q, it's really trying to solve this system of equations using something like value iteration, but with extra stochasticity, and so it also suffers the same problem. It doesn't necessarily converge. There's not really a unique solution to Q star because you can have different Nash equilibria that have different values.
Right.
So there isn't really much hope of converging to the answer because there isn't the answer. The policies cannot be computed independently, right? So Nash equilibrium is really defined as a joint behavior, and so we can't just have two different players computing Q values. Even if we could compute the Q values, it wouldn't necessarily tell us what to do with the policies, because if you take two different policies that are both half of a Nash equilibrium, two halves of a Nash equilibrium do not necessarily make a whole Nash equilibrium.
Right.
Because they can be incompatible. So, so far so good, right?
Yeah. I can't wait to see what happens next.
The update is not efficient unless P equals PPAD, which is to say computing a Nash equilibrium is not a polynomial time operation as far as we know. It is as hard as any problem in a class that's known as PPAD. And this is actually a relatively recent result in the last 5-10 years. And this class is believed to be as hard as NP, so possibly harder. So it doesn't really give us any computational leverage to kind of break it down in this way. So that's unfortunate. And finally, the last little hope of, maybe we can define this kind of learning scenario using Q functions the same way we've been doing. Q functions are not sufficient to specify the policy. That is to say, even if I could do all these other things, efficiently compute a solution of, build the Q values, make them so that they're compatible with each other, and now I just tell you, here's your Q function, now decide how to behave, you can't. There's not enough information.
You're depressing me, Michael.
Yeah, so this is kind of sad. We go to the general sum case, which in some sense is the only case that matters because zero sum never really happens. And what we discover is that we seemingly lose all the leverage that we have in the context of Q-type algorithms. And that's where we'll stop.
Oh, so we're going to end on a high note.
No, maybe we should say something positive before we depart.
Let's do that. Come up with something positive to say.
Okay. So even though things are kind of grim with regard to solving general sum games, there are lots of ideas that have proven themselves to be pretty useful for addressing this class of games. It is not the case that any one of them has emerged as the dominant view, but these are all really cool ideas. So here's one. You can think about stochastic games as themselves being repeated. So repeated stochastic games. We're going to play a stochastic game, and when it's over, we're going to play it again. And that allows us to build Folk Theorem-like ideas at the level of stochastic games.
Oh, that's cool.
And so there's some efficient algorithms for dealing with that. So that's one idea. Another one is to make use of a little bit of communication side channel, to be able to say, hey, other player, here's this thing that I'm thinking about. And it's cheap talk in the sense that it's nothing that's being said is binding in any way, but it gives the two players an ability to coordinate a little bit. And you can actually ultimately compute a correlated equilibrium, which is a version of a Nash equilibrium that requires this a little bit of coordination, but can be much more efficient to compute. And you can actually get near optimal approximations of the solution to stochastic games using that idea.
Yeah, that's cool. Didn't I do some work in this space?
You did. That's where I got the idea from.
Oh, okay.
There's some work by Amy Greenwald looking at how correlated equilibria play into stochastic games, and then your student Liam and you developed a really cool algorithm that actually provably approximates the solutions.
Nice.
Another idea that I've heard a lot about lately that I really like is the notion of a cognitive hierarchy. The idea that what you're going to do is, instead of trying to solve for an equilibrium, you think about each player as assuming that the other players have somewhat more limited computational resources than they do, and then taking a best response to what they believe the other players are going to do. This turns out to be a really good model of how people actually play when you ask them to do games like this in the laboratory.
Huh.
Yeah, the good news about this idea is that because they're best responses, they can be more easily computed. It's more like Q-learning and MDPs again, because you're assuming that the other player is fixed.
Okay, how about that?
And the last idea I want to throw out is the notion of actually using side payments, so that the players, as they're playing together, can not only take joint actions, but they can say, hey, I'm going to get a lot, but if we take this action, I'm going to get a lot of reward. I'm going to give some of that reward back to you. And that'll maybe encourage you to take the action that I need you to take so that we'll both do better. And so there's this lovely theory by a father and son duo that they call COCO values. COCO sounds awesome, but it stands for cooperative competitive values. Mm-hmm. And so it actually balances the zero-sum aspect of games with the mutual benefit aspect of games. So it's a really elegant idea.
So basically, the problem isn't solved, but there are lots of cool ideas that are getting us close to solving it.
That's right. Yeah. So even though the one player and the zero-sum cases are pretty well understood at this point, the general-sum case is not as well understood, but there's a lot of really creative ways that people are trying to address it.
So that is good news.
Okay, Charles, what have we learned? And I mean specifically in the context of this Game Theory 2 lesson.
That's a good question. We learned about Iterated Prisoner's Dilemma, which turns out to be cool, and it solves the problem. And we learned about how we can connect Iterated Prisoner's Dilemma to reinforcement learning.
What do you mean?
Through the discount.
Yeah, so I think of that as being the idea of repeated games.
Right. Let's see. What else have we learned? So we learned about Iterated Prisoner's Dilemma, which allowed us to get past this really scary thing with repeated games, connected it with reinforcement learning, with discounting. And then we learned other things, like, for example, I don't remember. What did we learn?
Well, so the connection between Iterated Prisoner's Dilemma and repeated games was the idea that we can actually encourage cooperation. And in fact, there's a whole bunch of new Nash equilibria that appear when you work in repeated games. And that was the concept of the Folk Theorem.
Right, the Folk Theorem. So the Folk Theorem was really cool. And this whole notion of repeated games really seems like a clever way of getting out of what appeared to be limitations in game theory.
Right, yeah, in particular by using things like threats.
Right, but only plausible threats.
Right, so that was the next thing we talked about, the idea that an equilibrium could be subgame perfect or not, and if it wasn't, then the threats could be implausible, but in the subgame perfect setting, they're more plausible.
Right, let's see, and then we learned about Minmax Q.
Well, there was one last thing we did on the repeated games, which was the computational Folk Theorem.
Yes, you're right. So basically what we learned is that Michael Lippmann does cool stuff in game theory.
Or at least he does stuff that he's willing to talk about in a MOOC.
Yes. So that's there's actually a technical term for that, right? MOOC acceptable research.
Oh, I didn't know that.
Mm-hmm.
So all these things are, by virtue of the fact that they showed up in this class, MOOC acceptable.
Exactly.
All right, you're right. Then we switched to stochastic games.
Mm-hmm.
And they generalize MDPs and repeated games.
Mm-hmm.
Anything else?
Well, that particularly got us to Minmax Q, and then eventually to Nash Q. But despite the fact that Nash Q doesn't work, we ended up in a place of hope.
We end with some hopefulness.
Yeah, and I think that that's actually a lesson for the entire course. That at the end of the day, sometimes it doesn't always work, but there's always hope.
We don't give up, and that's how research works. Even when we have impossibility results for things like clustering or multi-agent learning and decision making, we still keep struggling forward.
And keep learning. And isn't that what's really important? I think so.
It's important for us, and it's important for machines.
Yes, that is beautiful. I feel like we've made it to a good place, Michael. Perhaps we should stop.
Well, it has been delightful getting to talk to everyone, and it has been very fun getting to talk with you, Charles. And thanks to everybody for making this happen.
I agree. And we have one more chance to talk with one another as we wrap up the class. And I look forward to that. So I will see you then, Michael.
Awesome. Do we get to see each other in person for that?
We get to see each other in person for that. That'll be fun.
Yay.
Okay. Well, bye, Michael. I'll see you next time.
Bye. See ya.
Bye-bye.